Alright, what's up? Hey, it's Mr. K doing another video for AP Physics 1 and C. All these momentum videos can be used for Physics C or Physics 1, it's all good. So, we're looking at another one. We're going to work with impulse today. And so, impulse is that change in momentum that we're going to have. And so, one thing that I like to do with Physics C is to take them outside and fire some rocket engines off. So, here's a slow motion video of a model rocket engine firing off, and we're going to talk about the impulse that we can use with that and what impulse actually is. So here's a slow-mo video, or I think this is going to be a normal video, and then they're going to slow it down. So let's play the video. Well, now let's play the video. Okay, so this is a solid rocket engine. It's firing. It ignites. And when that solid rocket fuel ignites, it just burns as fast as it can possibly go. It's a controlled explosion. You see that hot gas being shot out the back, and well, this is a clear rocket, and it's kind of cool. Here's slow-mo. Really slow-mo. There's a circuit here that gets it hot enough. So if I pause it right there, what we can see is all this hot gas being shot out the back. Well, you know, if you thought about the problem in the beginning, really all this hot gas is that fuel that's going through that chemical reaction, heating up, exploding, releasing all of its chemical energy, turning it into kinetic energy. And now all this hot gas has this motion backwards. And so we have this motion that all this hot gas is moving out of the back of the engine. Well, in order for it to have gotten that velocity, it had to speed up, right? So we had to have some kind of acceleration. Well, how do we get acceleration but from forces? And so there's this force on this hot gas, all this stuff shooting out the butt of the rocket engine. And according to Newton's third law, there has to be a force the other way, which is going to be the force of the hot gases that are pushing on the rocket engine itself. So we have these two forces that are the same force, really, the same size. And one is on the hot gases, and the other one's going to be on the rocket engine itself. And that's what's going to propel our projectile forwards, like a bullet or a rocket or a jet plane. Those hot gases are shoved out the back of the jet plane. And let's keep on watching this video, see if anything else is going to happen here. Well, that's about it, but it fires on through. Burns all out. And at the very end, you're pretty much done, and you have a little at the end because you need to pop out the parachute. So, some of these things are cool. Anyway, so back to getting back on topic. We have this thing that we call impulse. Impulse, I'll write some notes down for you. Impulse is basically a change in momentum. That's what it is. It is a change in momentum, and usually we're talking about is some kind of change in the velocity of some object. All right. So impulse is, again, a change in momentum. Most likely we're talking about the change in velocity. I'm not really sure how we can talk about the change in mass with momentum. So change in velocity. The way that we get it is we apply a force for a period of time, and as we did in the last video, force is going to be in newtons, time is going to be in seconds, and so an impulse is going to be a newton second. All right, so we could have impulses to speed us up, we can have impulses to slow us down, kind of like work. You could have work to speed something up, work to slow something down, but work gave us energy, whereas impulse, forces times time, not distance like work is, are gonna change our momentum. And momentum is definitely gonna care about direction, whereas energy really doesn't. So work, the force and the direction of that force would really matter, but when it gets down to kinetic energy, who cares about the direction as long as we're moving? With momentum though, we kind of care about the direction. So let's kind of take a look at what's going on here. What I know from class that I've done this before is that with a rocket engine, solid rocket engine, we usually work with like C65s. It does put out a lot of force from that rocket engine as it burns on through, you know, compared to the mass of the engine. It's a lot compared to the mass. But if you were going to guess how much force a little model rocket engine put out, you're probably going to be wrong, because when we put this thing on a force plate and we fire it off, the force that you're getting is only about like 4 newtons of force. Okay, so when this thing's firing off, there's only about 4 newtons of force on average, maybe around 3. So that's not a lot, but it's a lot for how much you're trying to move. And then depending upon the size of the rocket engine that you have, the burn time is going to be anywhere from like 2 to maybe 4 seconds. So let's say that this thing burns for like 2 seconds. Okay, so what we usually would see in on our data is we would take data of the force of this rocket engine as time goes on. So we'd have a force time graph. Okay, and so real data, you know, just kind of mimicking what I would see whenever we did this outside in Physics C, is we would get a little bit of nothing. Here's 0 force here, and then I fire the rocket engine off, and then the thing peaks up. It goes, poof, and then it kind of drops down a little bit because you have that first initial jolt, and then it kind of stays constant, and then it goes down, stays constant for a while, and then you have a little, which is that last little burn. If you've ever done model rockets, it's that last little puff that knocks your parachute out. So I'm not really concerned about this little thing, but it's all this that I care about. And so this is going to probably go to around 4 newtons of force, and so that burn time is pushing those hot gases out the back, and at the same time it's pushing that rocket engine and whatever it's attached to forwards, right? So looking at this, impulse is the product of force and time. On this graph, the product of force and time is going to be the area of that shape. And we can make it simple. We can just make it like a rectangle, right? And so if we took the height of the rectangle, which would be 4, and we multiplied by the base of the rectangle, which we said was 2 seconds, then we get an impulse of 8 Newton seconds, which is exactly what we would get with our equation. I'm just trying to show you the graph. So by this graph, by the data that we I kind of made it up here, but that's basically what we will get in class. We've got about 8 Newton seconds of impulse, of momentum change. And so, you know, here's a rocket, and our rocket would be sitting there with that rocket engine in the bottom of it. And we got some fins on the rocket, I guess. And with this rocket, you have, you know, about 2-3 seconds of burn time, and that rocket engine forces those hot gases out the bottom, and in turn, it's going to make that rocket go upwards. Okay, and so the trick is, you know, you got to figure out, well, what's the deal with these forces involved? Well, here's one thing that we can guarantee. If your rocket had a weight of 4 newtons, your rocket's not going anywhere, right? So look, you got to look at the free body diagram. So if we have this free body diagram, we have this downward force of, let's say, mg, and we're going to have this upward force of the rocket engine. If those two things are the same size, you're not going anywhere. You're just gonna sit, right? If your force of gravity is bigger than the rocket engine's force that it can provide, you're gonna need normal force, and you're still gonna just sit there. So ideally, you're gonna want some amount of rocket engine force that is greater than the force of gravity on this rocket. So if we're putting out a impulse force from this rocket engine of 4 newtons, we want something that's less than that for the rocket itself. So usually rockets are very, very light, maybe like 25 grams, 30 grams, 40 grams. So let's say this thing is 25 grams, or 0.025 grams total, or kilograms total, right? If we find the mg of that, that's going to be multiplied by 10, so we have 0.25 newtons. Well, that's good, you know. So we have this impulse force times time. This force of the rocket engine is 4 newtons, and we have this force gravity, which is 0.25 newtons. Well, that's an excess force, that's a net force upwards of 3.75 newtons. That's good. What does that say for our rocket? Well, that means if we have excess force, then we can do F equals ma. And if I know that the force is 3.75 and the mass was, what did we say it was, 0.025, then that means that my acceleration would be 3.75 divided by 0.025. And so that gives me an acceleration of 150 meters per second squared. That's a lot. That's a ton. That's 15 G's. But that's, you know, if you've ever fired off a rocket, they go really, really fast. And that's why. It's because, you know, although our measured force from this rocket engine is so small, the rocket body is very light. And so if we know that this burn happens for about 2 seconds, we can say, all right, after 2 seconds of acceleration of 150 meters per second squared, we should be getting to about 300 meters per second. Now, that's a lot. Fortunately, we live, well, unfortunately, I guess, well, both. We have air. And so guaranteed your velocity will not get to 300 meters per second because you have air resistance, but theoretically, with no air in the way, you're probably going to get that fast. Okay? So impulse is just a change in momentum. It's not a terribly new thing, but you do need to consider direction. So one last thing that I would want to run with you is, let's say we have a ball, simple ball drop problem, and this ball falls down and it hits the ground and it bounces up to maybe half the height. Okay, so let's say it falls down, maybe we have a 2 meter drop and it falls and bounces up to a 1 meter height. Okay, so if we look at this, we could look at it in terms of energy, we can look at it in terms of momentum. Well, obviously we lose half the energy here in the bounce, right? Because it drops from 2 meters, we'd bop up to 1 meter. So we lose half the energy. Well, what about momentum? What about impulse? Was there impulse on the ball? And so if we look at this, we probably want to figure out a little bit about what happens to the velocity before and after this collision. So let's do a little bit of energy. We start off with some kind of potential energy due to gravity. We end up with some kind of kinetic energy down on the ground, right? So we know that it's mgh is equal to 1/2 mv squared. And the m's cancel out, and so we get like a 2gh. Just doing this kind of fast because we've done it a bunch. We got a 2gh for our velocity here. So 2 times 10 times 2 again for the height, square rooted 40, gives me 6.324 meters per second on the strike. All right. Change h to 1, we've got 2 times 10 times 1, so 20, and then we've got to square root that. And I get about 4.47. So 4.47 meters per second, okay, is this upwards velocity on the bounce. You got a downward velocity before the strike, 6.3 meters per second, 4.47 on the way up. So as far as this ball goes, let's say it's a 0.5 kilogram ball. And so now we can talk about, well, we can talk about energy loss, but let's talk about momentum. As far as momentum goes, was there an impulse? And a student should say, well, yes, there was an impulse. And I would say, how much? And you would say, okay, well, you had momentum coming in, which was the mass times the velocity of the ball. And you had a momentum going out, which was the mass times the velocity of the ball. And so we would say, all right, well, we have 6.324, cut it in half, and we have a momentum incoming of 3.162 Newton seconds. And then you'd have a 4.47, cut it in half, and you'd have a 2.235 momentum of Newton seconds. And so you'd say, well, yeah, Mr. K, the change in momentum, that's impulse, right? And so we would just take the 3.162 minus 2.235, and my change in momentum would be 0.927 Newton seconds. And I would say that's fantastic, except that's as if it hit a sheet of rice paper and it slowed down and it was still moving in the same direction because you forgot that momentum cared about direction, right? So it's actually not this. It's more. Because what happens is you have to change the momentum going downwards to the momentum going upwards. So it's not a subtraction of the two. It's a negative coming in and a positive going out. You got to add the two totals together. So a minus minus is a plus. So 3.162 plus 2.235. The total change in momentum is 5.4 Newton seconds. And if you do it that way, the force required to change that is much higher. The only thing that we would need now is the time of the impact. And I don't really have that. So either we make up a number, which I guess we could, or we just stop the problem. Let's just make up a number real fast. The time of the impact, let's say it's like 0.1 seconds. And if we do that, we can now find out the force, because the change in momentum is a force times the time, right? So 5.4 is equal to the force that we want times the time, 0.1 seconds. Let's just move this over. It's going to be 54 newtons of force. And so, because we have momentum downwards and now we have momentum upwards, that change is a bit bigger than we thought it was in the first place. Okay? Impulses change momentum. We're going to use that a lot too. We're going to practice a lot more with it. But this will be the end of the video for now. See you later.